Okay. Hi, Walter.
Yeah. Hi, Mr. Douglas.
Um, okay. Alrighty. How are you doing?
Oh, pretty good. How about you?
All right. You been busy?
Um, Less this week.
Less this week. That's good.
Um, Logan is stuck in traffic. He was coming to school today, but he got stuck in the 1 inch snow traffic that we have.
Okay.
Um, so
Yeah, so we'll start and he'll catch up.
yeah, it, I talked to him like 30 minutes ago, but I don't know if he is close or not.
Okay, that's fine. And what did you have to do this morning, Ryan?
Uh, what? Oh, we
You
had
had an
a
assembly or something, you said. You had to be in an
yeah.
assembly with me?
Uh, yeah, when I usually send it in the morning, we our upper school head had us come to like an assembly, like all the upper schoolers, and she talked to us about getting home safely and like
Oh,
that we were like dismissed at a certain time, but like we can go. And I
got
couldn't
it.
send it to you, but I just
So
sent it
that's
to
all
you.
right. That's all right. So it's all the weather. It's all that one inch of snow.
Yeah, it's getting a little. This is more than I've ever seen.
Uh-huh.
But they said it would only be 1 inch, but it doesn't look like that. Uh,
Okay.
and people don't drive very well here. I have this is my work. This is some of my work for
Yeah,
from last
okay.
night.
Just send it in.
I have I have a scanner right over here, and I can try to send it to you.
Okay. That's fine. You just do it after class.
Okay.
Um, all right. I have a quiz for you guys. Quiz 6. It's under today in e-college, and the password is dilation. Dilation.
Okay.
Mr. Douglas, I have a fire drill right now.
Oh,
Alright, so I'll be back.
okay.
People go outside on this.
We gotta wait.
Uh, yeah. Uh,
Yeah, I'm back.
Okay. I put it on for 10 minutes. I wonder if that's going to mess you up.
Oh, I didn't start it yet since I was still loading.
Oh, okay. You know what? Do it later, Walter.
Okay.
Do the quiz later. And okay, I'm glad you didn't start. Ryan is probably almost finished.
Yeah, I'm done.
Okay, great. And submit it. All right. Tell Logan to do his quiz later too. All right.
Okay.
Later today sometime. Takes 10 minutes. Okay. Because So test 2. I haven't made it yet, but I will after class today. And I'll make so I'll send that to your tech leads, and you need to schedule it sometime by next Friday, same as last time. And I'll make a prep sheet too, like I did last time, and I'll send that to you. Okay? That's my announcement. Let's see. And then so next week, so next week we'll have class through Friday, and then the week after we won't, when Fort Worth Country Day's on vacation. Yay. Okay, so transforming graphs. I would like you, so I'm going to share the correct screen so it gets, so I'd like you to log into Adobe Connect Friday, and I figured out what the matter was, why I couldn't stop sharing. But for recording purposes, I have to share the correct screen, so I'm going to do that now. I have to share that in BlueJeans. Okay, that's the right screen. And they say share entire screen. Okay. And then I'm going to go into Adobe Connect. Because here it minimized it. That was the issue. And when you guys log in, I'm going to make you presenters. Okay. So you're both presenters now. And I would like one of you to show me number 4, what you did on number 4 of transforming graphs.
I guess I'll do that.
Okay, Ryan. So can you share your screen on Adobe Connect?
I can write it on the board because that's one of the files that I needed to scan.
Oh, I see.
Yeah.
Okay, that works.
Here, let me get the right screen up. Yeah.
Okay. Yeah, do that. Okay, that's fine. Okay, we can see.
Oh no. One sec.
Okay. Yeah, start towards the top so you have room.
Mr. Douglas, it's kind of hard for me to see since.
Oh, it's too hard.
Okay.
Yeah, okay.
I'll just explain, or I'll just verbally explain it then, because I'm pretty sure Walter got it.
Okay.
Because this is, I think we went over this one in the last class.
Oh, okay. Well, no, I don't. Yeah, we went over one that's similar. Yes.
Yeah.
Let me get my file up, and we'll do it that way. I'll share my screen, and as you talk it through, main display. Okay, sharing that. I'm sharing mine, and here's the file. Can you see that?
Yes.
Okay. Okay.
So, since we have an intercept at 12, and that's one of our maximums, I started out with y cosine, or y equals cosine x.
Okay.
And then I did the t parentheses xy parentheses.
Let me get a math type to make it easier. Okay. T of xy, yes,
Uh-huh.
equals what?
3x over pi,
Okay.
because the period is 6.
Okay. 3x over
So-
pi.
Yeah.
Okay.
And then 4y plus x, or plus 8.
4y
Sorry.
plus, you don't mean x. 4y plus
8. Sorry.
8. Okay. All right. Save it. Make sure. Yeah. Is that correct?
Yes.
Okay.
At least I think it is. And then the inverse of that would be,
Just a second.
yeah.
Okay. Is what?
Is pi over, or pi x over 3.
Okay.
And y minus 8 divided by 4.
One second. Minus 8 divided by 4.
Hey, you need to take the quiz afterwards.
Okay. Is that correct?
Yes.
Okay. So now you substitute that into y equals cosine x and continue. Walter, is that what you got?
Yeah.
Okay.
Wait
So,
a second.
Let's finish.
Wait.
Sorry? Walter, Ryan, are you saying something?
Yeah. For the inverse, I read off the wrong one.
Oh.
The y, just for the y, it's actually. No wait. No, yeah. Never mind.
No,
Sorry.
y minus 8 over 4
Yeah,
is
that's
right.
right.
Yeah. Okay,
I
so then the equation becomes, one second, y minus 8 over 4 equals, so y minus 8 over 4 equals cosine of parentheses, fraction, pi x over 3. Pi x over 3. Okay.
Yeah.
Yeah. And then you solve that for y, and you get y equals 4 times, yeah, so I can copy and paste that over here. We want to solve for y, so y is going to be, y is going to be 4 cosine that plus 8. Get rid of this. Okay, correct?
Yes.
Okay, and we can check it. And that's, Walter, that's what you got too, right?
Yeah. Well,
Okay, good.
yeah, I
Um,
did sine instead of cosine, but I made an arithmetic error in there.
Oh, okay. All right. Cosine was a good choice because of
Yeah.
where it starts. Okay. Well, Logan, welcome.
Hello.
Okay, so there we gave a quiz. You can take it later today sometime, okay?
Okay.
And I announced that I announced about test 2. That's coming to your tech person today and later today, and you need to schedule it. by next Friday, and I'll send you a prep sheet like I did last time.
Okay.
Same thing. Okay. So Walter, can you share your screen now and show us what you did with the hyperbola? So let me
Yeah.
stop sharing. Now I realize, see, it minimized it it minimized the add-in. So I need to stop sharing. Okay, which I did. And now, Walter, you can share yours.
Okay.
And Logan, I'm going to make you a presenter. Yeah. Okay.
I think it would be easier just to explain it since
Okay.
I can't really get it to load.
All right. So I'll go to my file and so I need to share my screen. Okay. So can you see this?
Yeah.
Okay. Okay. Talk to me.
All right. So, I recognize that the midpoint between the two vertices of the hyperbola is 6 comma 4,
Okay.
and
So the
so
center, so to speak,
yeah.
is 6, 4.
So in the original x squared minus y squared equals 1, the center is the origin.
Right. So
So
original. Just a minute. So let's write original is give me a second. X squared minus y squared equals 1. X squared minus y squared equals 1. Okay? Right?
and the center for this original one is the origin.
Right.
And I also noticed that there was a horizontal shift of 4.
Okay.
Horizontal stretch of 4, sorry.
Now, how did you know that?
Because the distance from a center to the vertex of the original is 1, whereas the distance from the center to, yeah, it's 4 for the other one.
Okay, distance from center to vertex. Okay. Okay.
So then I let t of xy be
Mm-hmm.
4x plus 6, comma 2y plus 4,
Okay.
where the 2 is due to the slopes having plus minus 2.
2x plus 6. And
4x plus 6, sorry.
4x plus 6. And what's the y again?
2y plus 4.
Y plus 4. Okay. All right. Explain that one more time. Sorry.
So the 4x comes from the horizontal stretch of 4,
Mm-hmm.
and the 6 comes from translating the center to the new center,
Right.
and the 2 comes from the asymptotes having slope plus minus 2,
Right. Good.
and then the 4 comes from translating the y center by 4.
Good. Good.
Okay, so then I set, so then t inverse xy is x minus 6 over 4, comma y minus 4 over 2.
Right. Give me a second. So T inverse is x
minus 6 over 4.
over 4. And y what?
Y minus 4 over 2.
Y minus 4 over 2. Okay, is that right?
So then I just took the x and y and then put
And
them into the
substituted
original
into
equation.
this. Okay.
Yeah.
So x minus 6 over 4 goes here, and y minus 4 over 2. So, let's just replace the x with a fraction. Oh, we need parentheses too. No, we don't. Yeah, we need it on top. X minus 6. Actually, it would be better to. Sorry. It would be better to do the whole thing in parentheses and make this x minus 6 over 4. And then that's a good template for this. And it's y minus 4 over 2. Y minus 4 over 2. Got it. Okay. All right?
Yep.
Okay. Questions? Ryan, Logan?
Not really, actually. I got the horizontal stretch incorrectly, but I see what I did wrong.
Okay. And Ryan, you good?
Yeah, I just messed up on identifying one of the stretches.
Okay. All right. That's good. I'll send this because, now it has it. You can check it, although I think you probably have it. Okay, good. So you notice that this method, works even for non-functions. It gives you the same result as you're used to. All right, so we're done with that. There's that. The next thing is this translational symmetry, and I wanted to discuss number 3. I think we can just discuss that. Okay. Why do you think they're called tilings for A?
Because these patterns are usually used as decoration for like floors or ceilings, and they usually use tiles to
Right.
make.
Okay, and now we have these interesting patterns, tessellations, which extend infinitely in all directions. You have to imagine that. And so, Logan, can you describe for me one symmetry? You know what? Let's see. Let's do the second one because that's, I think, easier to talk about. So this has, and I'll look at what you did for the others. Here's octagons and squares, what it's made up of. Regular octagons and squares. I think it's called a semi-regular tessellation because it has 2 different kinds of regular polygons. So we're just going to rotate around. Describe for me ones. This got lots of symmetry all over the place. So Logan, give me one.
It's got twofold symmetry.
Twofold rotational symmetry around what point?
I said it could either be the center of any of the octagons in the middle line,
Okay.
or it could be on one of the lines that runs between the
Okay. If we take the center of the octagon, is that just twofold?
Oh, it goes up also, so it's fourfold.
Yeah, it's fourfold. Yeah, that's right. You have a fourfold on the center of the octagon. That's one. Okay. We're just going to go through a few. Ryan, give me another one.
Are we just talking about the rotational ones?
Any symmetry at all.
All right, you said the octagon metal and
the octagon.
Okay. A line of symmetry where any of the octagon side meets each other.
Yeah. Okay. So like for example, a vertical line of symmetry here.
Or like a horizontal one. Right. Yeah. Like right there.
Okay. Okay. Good. Walter, give me one more.
There's a line of symmetry through the opposite sides of any octagon.
Okay. Right. So here and here. Okay. Good. Good enough. Okay. History. Yeah. So are there any questions on number 2, which is here? There's a lot of questions or comments.
I have a question.
Yeah.
On about that third line of the equation where he puts he adds in a 3uv.
Yeah. Here.
Yeah.
Here.
Was that one of the equation or was that something that we had to explain?
Well, you should know what's happening. How you should know how to get from the line above to this line.
Okay.
Can you explain that?
I can't. I'm not sure about the 3uv, but I do know that he just distributes the square to u plus v.
Yeah, so that's u squared plus 2uv plus v squared. So what happened here? How come I don't see just u squared plus 2uv plus v squared? What do you do?
Did he also substitute in or I'm not sure.
Okay, Logan, do you know? Did Logan go?
He had to step out to talk to his parents, I assume.
Oh, okay. Walter, what's happening here?
You just add minus UV and 3UV together, and that gives you the 2UV.
That's right. So instead of 2UV, you made it 3UV and then a minus UV. And did that for a clever reason. Do you see why that was done?
Yeah, it's a sum of cubes.
Yeah, because the u cubed plus v cubed factors into u plus v times u squared minus uv plus v squared. So he wanted to get that part in there so he could get it to u cubed plus v cubed.
Okay.
Pretty clever stuff. Okay. So that gets us to this.
Mm-hmm.
And then the other brilliant thing he did was he made 2 equations. He said, basically, I want this thing to be 0. So I'm gonna just make that 0, and then if that's 0, 3u plus 3uv plus p is 0, then this whole term goes away. And then I'm left with u cubed plus v cubed equals q. So he kind of had the idea that it's going to be the sum of cubes. He has some idea of the solution, which is crucial for doing that. Okay? So then you have these 2 equations, and solving them will give a solution to this. And then he has to solve them. So, okay, so you see this step here?
Mm-hmm.
So he solves this for v, plugs it in to the other, and gets this, and then multiplies both sides by u cubed and gets this, and then clears the fractions. Well, no, it doesn't clear the fractions. Puts it in this form, and it looks like a terrible 6-degree equation, but it's a quadratic in u cubed. That's the amazing part.
Okay.
Okay, so it's a quadratic in U cubed. You use the quadratic formula, and you solve it, and then you've got U cubed. But then, of course, you need U, so you take the cube root. That's where the cube root comes in here. So there's some steps to fill in here. You know, it's to use the quadratic formula to solve this for U cubed. And then once you have that, you can solve for, you can use this, right? You want to solve for V also. Or this, Q plus V cubed equals Q. And you can use this equation to solve for V cubed once you have U cubed. And then take the cube root to get V. And so you have the sum of these two cube roots.
Okay.
All right? So that's what's going on. And that's the solution to... and then this note here is important at the end. See, that these were important equations. The problem was too hard without having some idea of what the answer would be. So the answer is, the sum of these things.
Okay.
And then this part is interesting. As long as P and Q are positive, you can always solve for X. Right? That makes sense. And we're solving an equation of this form. X cubed plus PX equals Q. With things positive. And then I'm going to have you read some of the rest here for homework, but I just want to talk for a minute about what happens here. And this is kind of interesting. 16th century mathematicians generally avoided the appearance of negative coefficients. They were unhappy, even in the 16th century, with negative numbers. Some people were, but were comfortable, but some people were not. So they tried to avoid it. So if you had an equation like this to solve, x cubed minus 6x equals 20, which looks to us like the same form with a negative 6 coefficient, Del Ferro in those days would have written it this way and started all over. For him, it's a completely different situation. So that's an example of the usefulness of negative numbers. That's why a lot of times teachers say, you'll find out why this is useful later, and then they never come back and tell you. Here's one example. There are a whole bunch, but it's good to think about. Why are negative numbers useful? So here's one, and for us, it's very easy. We just write it this way and substitute negative p for p, and we get this kind of situation. So the old situation is a solution of this, and the new situation now has some minus signs in it. That's the difference, and it's a solution of an equation of this form. Okay, so you can look that over. So what I'm going to have you do is look at 4, read 4. I'm not going to talk about it now, but it's interesting. Read 4, which is about how complex numbers came about in the first place, why somebody wanted to deal with them. And then the geometry, which was discovered 100 years later. And this was how the discovery went. But then we'll talk about how to use this. So those two things is what I want you to read, 4 and 5, 3, 4, and 5. All right, enough said about that. And then the last thing we're going to talk about, we're going to go through 1 through 5a. So this is a new handout, a new document, and I'm going to go through some of it together with you, and we'll make needed edits as we go. So there are things to fill in. All right. So the next topic that Walter in particular wanted to do was 3D transformations and symmetry. So how much exposure have you had to 3D polyhedra, let's say? Did you study that in geometry at all?
I can do AMC and AME problems over them.
Okay. Okay, good. Ryan Logan?
Not that much.
Not really.
Not that much. Okay, so good. This is new and interesting. And we live in a 3D world. We should do more of this. A polyhedron is a 3D figure bounded by polygons, and the polygons are called faces. And the sides of the polygons are called edges in 3 dimensions, not sides. And vertices are still called vertices. Polyhedra are often named by the number of their faces. English words come from both Latin and Greek, so sometimes a different prefix is used. For example, a quadrilateral, quad is the Latin for 4. So a quadrilateral is a polygon with 4 sides, but they don't use a quadrihedron, they use a tetrahedron. How many of you have played Tetris? All right, so that's the 4, the 4 squares. A tetrahedron has 4 faces. Tetris from Greek. So here's a list of names. Tetrahedron is 4 faces. Penta is 5. Hexa is 6, as you might expect. Octahedron is 8. Decahedron is 10. Dodec is 2 plus 12. 2 plus 10 is 12. Dodecahedron is 12, and an icosahedron is 20. And the reason those are important has to do with something I'll talk about in a minute. So a regular polygon has all sides and angles congruent. The faces of a regular polyhedron must all be congruent regular polygons, and all the polyhedral angles. That's like a 3-dimensional angle. You can imagine, several a space enclosed by faces that intersect at a vertex, and those angles must be congruent also. The interesting thing is there are an infinite number of regular polygons, but there are only 5 regular polyhedra. And they are, I'll tell you, the regular tetrahedron, which is made up of 4 triangular faces, a regular hexahedron, better known as a what? 6 faces, 6 congruent faces.
Cube?
Cube, right. Hexahedron is a cube. A regular octahedron, which has triangular faces. It's like 2 square pyramids, one underneath the other. And a regular dodecahedron has pentagonal faces. And sometimes, since it has 12 faces, sometimes you'll find calendars, 3D calendars, with a different month on each face. I don't know if you've ever seen one of those, but they exist. And an icosahedron has 20 triangular faces. And those are the only regular polyhedra. There are only 5. It's kind of interesting. And then if you go into higher dimensions, they're called polytopes. Those you can't really see, obviously, but they're extensions. So a hypercube is a 4-dimensional cube, and there are some regular polytopes in higher dimensions as well. We'll skip those. All right. There's also another word that comes up, a deltahedron. It's kind of interesting. So it's a polygon, all of whose faces are triangles. You know where delta triangle? Delta is a change. It's a Greek letter, and it looks like a triangle. So that's why they're called deltahedron. Okay, isometries. This is where we're going to start thinking about isometries in 3 dimensions. So the most basic 2D isometries are these 3. There's a glide reflection too, which we use for a reason, but right now we'll just do those 3. These can all be done in 3D, but of course the definitions must be modified. And then here are some examples. So 2D figures sometimes have 3D analogs. And here are some examples. A triangle in 2 dimensions is kind of like a pyramid in 3 dimensions. A parallelogram becomes a parallelepiped, which has parallelograms for faces. It's like a slanted box.
Okay.
Rectangle is a rectangular prism, or I'm just going to call it a box. I mean, a standard box. A square becomes a cube. A circle is like a sphere. An ellipse is like an ellipsoid, which is, you study calculus, so when you rotate an ellipse around one of its axes, you get an ellipsoid. And when you rotate a parabola around its axis of symmetry, you get a paraboloid. And when you rotate a hyperbola in different ways, you can get a hyperboloid, and there are different ones. Okay, now we get to how do you define these things? So a 2D figure is reflected in a line. The reflection line is the perpendicular bisector of the segment joining any pre-image point to its image. That's important. Okay? Now, you're going to help me fill in the rest of this. The 3D figure is reflected in a what?
Plane.
Okay? So a plane of reflection. And can we make a sentence that's similar to this in 3 dimensions? You have to modify it a little bit. You can't just, replace the words. It's a little funny. So don't say anything yet. Spend about 30 seconds thinking about how you would phrase that in 3 dimensions. Or maybe it isn't. Okay, who's got an idea?
So I guess
Yeah.
you start out with the reflection plane.
Okay. Yes. Yeah, we can, so part of it is this part here.
Yeah.
This part we can just do this with. So is that true?
Yes.
Okay. It's perpendicular to it. How do you define a plane being perpendicular to a line?
Oh, if the line and plane meet at one point, or at only one point? No.
A plane is perpendicular to a line if
a line on the plane is perpendicular to the other line.
Which line on the plane?
Any line.
All lines?
Yes, if any line in the plane passing through the point of intersection perpendicular to a line. That's important because you can have some lines perpendicular always, but not, so the key word here is any. Right? Because here, look at me. No, you can't see me. Or can you? Can you in blue jeans? No, you probably can't because I'm sharing this.
We can.
We can.
You can? Okay. So if I have a line that's oblique to my plane here, then there is a line in the plane that's perpendicular, but it's not any line, just one. There's always one line. Okay. So that's the first part, but how are we going to say something that's similar to this part? Using the idea of you know what? I didn't put that sentence in, so I'm going to put another sentence in up here. Yeah, I should have done this. So I'm going to add a sentence here. Any point on the perpendicular bisector. This we've done before. On the reflection line. Let me put it that way. On the reflection line is equidistant from the pre-image and image points. True?
Yeah.
Okay. Is there a similar sentence for 3 dimensions?
Any point on the plane is equidistant to...
Yeah, so that's still true. Except we just replace line with plane. Okay, so those 2 things will be. Can you see that? Can you imagine that?
Mm-hmm.
All right. All right. Rotation. A 2D figure is rotated around a point through a given. I'm just going to say directed angle. So we like we did positive and negative, and that takes into account clockwise or counterclockwise. All right. So what happens in 3 dimensions? A 3D figure is rotated around a what?
A line?
Yeah, around a line. And what's the line generally called? A what of rotation?
Axis of rotation?
Yes. Good. So that's the difference there. Good job. Translation. A 2D figure is translated by a vector, which specifies distance and direction. What about 3D?
It's also by vector.
Yeah, same thing. We don't have to make any change here.
Yeah.
Okay. There was a good, I'm reminded that, I don't know, there were some videos that were made on tape years ago that were good. I don't know if they've been modified for DVD, but I'm going to see if I can find some. There were some really good videos about 3D transformations, and I'm going to see if I can find them for next time. All right. So now we go to symmetry. So if I don't finish, I wanted to get through 5A today. We'll see what happens. I got 6 minutes left here. So symmetry. I've noticed that, the AL is used both ways. Some people call it reflection symmetry. Some people call it reflectional symmetry. Kind of depends. But here are some statements. I made some statements in 2D here, which are true. And I just copied them into the 3D part. But you need to change those, right? to make them correct. So I'm not going to talk about that now, but that's going to be part of your homework. Let's see if we have time to do. Let me see what else is going on here. Yeah, let me come back to that with whatever time is left. So that's the idea. You'll have to change these 3D statements to make them true. Okay? And then dilation. A 2D dilation multiplies the directed, so this is the way I said it. A 2D dilation multiplies the directed distances from a center to any pre-image point by a non-zero scale factor. So that means we can use a negative scale factor as well. Is that also true for 3D?
Yes.
Yeah, so we're fine. And then, so here's some examples. So I just wanted to do 5A. Here's a regular square pyramid. A regular square pyramid means, and I've noticed that on the web, some definitions are wrong. A regular square pyramid has to have a square base, yes, but it's not enough to have a square base. This is sometimes called the vertex. In this particular one, they called it the vertex is actually not so great because these are all vertices. So they called it the apex, which is maybe a better word. What has to be true for a regular square pyramid about this apex? I think I said that. Yeah, I said it here. So it has to be in the middle. It has to be right above the center of the square. So a 3D figure has an altitude, which is the line from the vertex, or the apex in this case, perpendicular to the plane, to the base, which is now a plane. And where that intersects has to be the center of the square. It has to be right above the center. So that will mean that all these are called lateral edges, which means side. So all these lateral edges are congruent. Whoops, didn't mean to do that. Okay, so can we describe the reflection and rotational symmetries of this pyramid? So again, don't say anything yet. Give you a minute to think about it, and then I'll take a symmetry from each of you. Okay, and we're just gonna, less than a minute, I think. And we're going to just take turns. So, Logan, can you start? Can you describe asymmetry of this regular square pyramid? Anyone?
It's got rotational symmetry. Wait. Yes. And the axis of rotation is through the top of the pyramid to the center of the base.
Right. So through that line, and how many fold?
4.
Good. So it's got 4-fold rotational symmetry around the axis that you described, which is the altitude of the pyramid. In chemistry, if you take more advanced chemistry, a lot of molecules have various kinds of symmetry. And I was talking to a chemist at one point, and they said, yeah, this molecule has a 4-fold axis, is what they call it, through these 2 atoms, and a 2-fold axis here, and stuff like that. So that's the way they talk about it. Okay, Logan, another symmetry.
It's also got.
I'm sorry. Ryan, yeah, Logan, you just went. Ryan is Ryan, give me a symmetry.
It has a plane of symmetry that's through the has a plane of symmetry along that runs through the apex and a diagonal and one of the diagonals
of the square base. Yes. Yeah. Yes, it does. Right. The plane goes. The plane contains the 2 opposite lateral edges, is another way to say it. It contains 2 opposite lateral edges and a diagonal of the square base. Good. Okay. Walter, one more.
There's a
Walter, you
plane of symmetry. There's a plane of symmetry that goes through the 3 points, the apex and midpoints of the opposite edges of the square.
Of the square base. Good. Okay. 10 o'clock. We're done. And I got through everything, so I'm happy. Okay. Good job, guys. Have a nice weekend. Enjoy yourselves. How much snow do you have, Walter?
We had 10 inches last week.
Oh my god.
Different from Fort Worth. Okay, take care. Bye.
Bye.
Yeah. We've got 2 and everyone's freaking out.
Right. Not the same. Not the same. Good thing we're not in Boston.
School's been canceled.
Yeah.
We're sitting here and Miss Wakeland, our upper school head, comes in while we're doing while we're describing some of the transformational graphs.
Uh-huh.
And I had to put it on mute, and she was talking to me asking if I had a ride back to my house.
I see.
Yeah, it was just funny because I was like talking to like 3 people.
Yeah. Multitasking big time. Okay. Take care, guys.
You too.
Yeah, you too.